Okay, so we in the last video we just had talked about this theorem where we can treat our sequences as functions. And what that means is that we can use our best friend when it comes to finding limits, and that's L'Hopital's rule. I don't know how to make the fancy thing over the O, just know there's supposed to be a fancy caret over the O. Okay, so let's look at an example. I don't know if this one has L'Hopital's rule in it necessarily, I'm just kind of picking one at random here. So let's do the limit of the natural log n divided by n. That did not come out the way I wanted it to. Better. Okay, so the limit as n goes to infinity, natural log n over n. So far, we don't have any properties that can take something out of a natural log like this, because we do not know what the limit of n converges to, right? The limit of n just blows up to infinity. So we cannot use the previous theorem, the one we did before this one. Instead, what we can do is we're going to treat, so if we treat n to be a continuous variable, then by the previous theorem, we can look at the limit. Now what's the limit as x goes to infinity of the natural log x divided by x? This is going to be L'Hopital's rule. Because if I plug x to be infinity up top, natural log of infinity blows up to infinity, the x in the denominator blows up to infinity, and I end up with infinity over infinity, which is a classic L'Hopital's rule thing. I know it's probably been a while since you've looked at L'Hopital's rule, but the way it works is you take the derivative of the numerator and then separately the derivative of the denominator. The derivative of the natural log x is 1 over x. The derivative of x is just 1, and then you take the limit of that ratio. But this is just the limit of 1 over x, which goes to 0. In other words, from the beginning, the limit as n goes to infinity of natural log n over n goes to 0. Cool. And I got one more example. This one's going to be a little bit longer. So let's look at this one. This should also be a technique that you saw back in Calc 1. Here we're looking at the limit as n goes to infinity of n plus 1 divided by n minus 1 all to the n. Great. So limit n plus 1 over n minus 1 all to the n power. I want to know, does this converge? And if it does converge, what is the limit? Messing everything up. Does this converge? And if so, what is the limit? Okay, so let's talk about it. Anytime you have the entire inside raised to the power n, the trick that we're going to be doing is doing log stuff again, because we have to get that n down, and the only way to bring an exponent down is by taking the log of both sides. So what we're going to do is we're going to rewrite that top part up there as the limit of a sub n is equal to the limit of just whatever we have, the n plus 1 over the n minus 1 all to the n. The reason I'm writing it like this, with just defining it with a sub n, is that now we're going to take the log of both sides, the natural log. I guess it doesn't really matter which log you take, but I like natural log better. So now it's going to be the limit of the natural log of a sub n on the left-hand side. That's going to be equal to the limit of the natural log of that awful thing, n plus 1 over n is minus 1 all to the n. All right, I can ignore the left-hand side for now because there's not really much that I can do with that. I'm just going to leave that as the natural log a sub n inside this limit. But this right-hand side, I can bring that n down as multiplication. So now it's going to be the limit of n times the natural log n plus 1 over n minus 1. Okay, cool. The next part that we're going to do is another L'Hopital's rule thing. Okay, so we have n plus 1 over n minus 1, and it would be very nice if I can figure out what the limit of the inside of that is. another part of it is that we have this n at the top. I'll go ahead and say that this stuff on the inside, n plus 1 over n minus 1, that converges to 1. But then the natural log of 1 is 0. We end up with n that's going to infinity times 0. That is not always what you think it's going to be. This does not necessarily go to 0, even though this goes up to a big number and this goes to 0. It may converge to anything, and I think you'll be surprised at what this eventually converges to. So we're going to have to do L'Hopital's rule here because we have infinities and zeros. The problem is that we don't have it written as a ratio yet, so let's just force it to be a ratio by looking at the natural log of n plus 1 over n minus 1 as the numerator, and then 1 over n in the denominator, like that. So we're just moving this into the denominator as 1 over n. Now what we have is we have 0 up top and 0 in the bottom. 0 divided by 0 is another instance where we can use L'Hopital's rule. To use L'Hopital's rule, we have to take the derivative of the top and the bottom separately. So let's do that carefully. The derivative of the top is going to be awful. Not only do we have the natural log, which is going to be a chain rule thing, but then we have this awful thing. It's going to be the derivative of the inside divided by the inside. Okay, I had to go back on my video because I realized I made some small mistakes. That was too much deleting there. This part here. Here we go. Starting back from here, right? So, like I was saying, it's the derivative of each of them for the L'Hopital's rule. We're going to take the derivative of that natural log and then divide it by the derivative is 1 over n. The derivative of the natural log is going to be the derivative of the inside divided by the inside. The derivative of the inside is going to be a quotient rule. So bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by that bottom squared. Okay, this we're going to have to do divided by the inside of that natural log, which is n plus 1 over n minus 1. Great. This whole thing here, the shaded part, is just the derivative of the natural log. So a quotient rule of the inside, bottom derivative of the top minus top derivative of the bottom over the bottom squared, divided by just the inside as is, n plus 1 over n minus 1. That's going to be divided by the derivative of 1 over n, which is negative 1 over n squared. Okay, looks awful. We're going to try and clean this up. First off, in the very top line, I have n minus 1 minus n plus 1. The n's cancel. I end up with negative 1 minus 1, which is negative 2. Then I have this negative n minus 1 squared in the denominator. This I'm dividing, which also you can think of as multiplying by the reciprocal. So this n minus 1 comes up top and cancels out with one of these n minus 1s. The n plus 1 is going to be divided now, so it goes in the bottom. So it's going to be that negative 2 divided by n plus 1 times n minus 1. I'm going to go ahead and leave that negative 1 over n squared alone that's already down here. So it simplifies down to be this. Okay, so this is still complex fraction stuff. I'm going to flip this over again. So the negative 2 will stay up top, but then this n squared I'm going to flip up. I'll go ahead and cancel out the negative signs too, because we don't need those. So in the numerator, all I have is 2n squared. In the denominator, I have that n plus 1 times n minus 1. All right. We still have it so that the numerator goes to infinity and the denominator goes to infinity. So let's rewrite this as the 2n squared as is, but let's multiply out that denominator. It multiplies out to be n squared minus 1. We're going to have to do more L'Hopital's rule. So we're going to take the derivative of the top, which is going to be 4n, divided by the derivative of the bottom, which is 2n. Maybe here you can say that the n's cancel out, and it's just the constant 4 divided by 2, which is 2, which means that it approaches the number 2. Now that's not quite the final answer, because if you remember from way back up here, this stuff that we've been working on is on the other side of the limit of the natural log of a sub n. So just to rewrite what we have right now, we have the limit of the natural log of a sub n is equal to 2. What we can do here is then we could move that natural log over to the other side by raising both sides as an exponent on e. Eventually what we get is that the a sub n is equal to e raised to the natural log of a sub n. So that's just kind of redefining a sub n. But remember that a sub n, or the natural log of a sub n, approaches 2. So what we get is e to the power 2. Whew, all right, this is a long one, and I know these suck, so make sure you really take some practice with these. But just to kind of think about it, we started off here, the limit of n plus 1 over n minus 1 to the power n. Almost any time you have an exponent of n, you have to do this natural log trick. Redefine what you have as just a setup or a sequence value here, a sub n. Take the natural log of both sides, bring the exponent down, play around with L'Hopital's rule until you get the limit of the right-hand side. Then that means that your original a sub n is going to be e to the natural log of your substitute a sub n. That approaches whatever you found here, so e sub 2. I hope it's crazy to see that this sequence that we started with, this thing, this thing approaches e squared. Weird, right? Math is crazy. Okay. We are still not done with section 1. There is still quite a few things to talk about. There's one more video that I need to make just for this section.